All right, let's talk about something that drives pretty much every Unity developer a little crazy at some point. You've got your character in the game, you've got it moving around, but the second you try to make it turn, it all falls apart. You know what I'm talking about, right? It gets all jittery, or it feels kind of floaty and disconnected, or maybe it just phases right through a solid wall. It's a classic headache, and honestly, it usually comes from one single common mistake. Today, we're going to fix that. We're not just going to make your character spin, we're going to make it rotate the right way, the professional way, by learning how to work with Unity's physics engine, not against it. So let me ask you this. When you want to make your character turn, what's the very first thing that pops into your head? If you're like most of us were when we first started out, you probably just reach right for the object's transform component and start messing with the rotation values directly. And hey, look, it kind of works, sort of. But what if I told you there's a much better way? A smoother, more reliable method that actually partners up with Unity's powerful physics engine instead of constantly picking a fight with it. This right here, this really breaks it all down. It's a tale of two methods. Over on the left, you've got direct transform manipulation. This is like you're a puppeteer with jerky strings, instantly teleporting your character's rotation from one value to the next. The physics engine sees this sudden, impossible change and just freaks out. It can't keep up, and that's where you get all those buggy collisions and visual glitches. But on the right, we have physics forces. This is totally different. Here, we're not commanding, we're guiding. We're applying a gentle, realistic rotational push, and we're letting the physics engine figure out the rest. It's the difference between a glitchy puppet and a smooth, believable object. Okay, so let's really dive deep into the problem. We're going to get into the nitty-gritty of what's actually happening under the hood when you write that one seemingly harmless line of code, transform.rotation equals whatever. Why does this one command create such a huge tug-of-war with the very system that's supposed to be making our lives easier? Here's the most important thing to understand. As soon as you add a rigid body component to your character, you hand over control of its movement to the physics engine. You've basically hired it to be in charge. So every single physics step, this engine is meticulously calculating things like velocity, collisions, gravity, friction. All this complex math. Then you come along with your script and you manually set the rotation. You're effectively storming into the room and shouting, "Stop everything, ignore all your math and calculations, just snap to this new rotation right now." This creates a massive conflict, a tug-of-war between your script and the physics engine, and the player is the one who sees the buggy result. That's where the jittering comes from, why objects pass through walls. You're literally fighting the system. So, if just forcing the rotation is the wrong way to go, what's the solution? Well, we have to start thinking a little more like a physicist. We've got to play by the engine's rules, and that means using the right tools for the job. Instead of commanding a rotation, we're going to politely request it by applying a specific, physically accurate force. It's time to talk about torque and rigid bodies. Think of the rigid body 2D component as your character's passport into the world of physics. Without this passport, your character is just a ghost. It's just a visual sprite. It can't fall with gravity. It can't realistically bounce off walls. It can't be pushed by an explosion. Nothing. This little component is what you add to tell Unity, hey, this thing here, it's a real physical object. Make it obey the laws of physics. It's our direct line of communication to the physics simulation, and it's the key to everything we're doing today. And the specific push we need to make things spin has a name: torque. It's actually a really simple concept. If you think about force as the push that makes an object move in a straight line, torque is the twist that makes it spin. When you use a wrench to tighten a bolt, you're applying torque. When you open a stubborn pickle jar, you're applying torque. In Unity, add torque is the official, physics-correct command we use to ask a rigid body to please start rotating. All right, enough theory. Theory is great, but let's actually make something happen. It's time to get our hands dirty and write some code. We're going to build a super simple player-controller script completely from scratch. So go ahead, fire up Visual Studio or your code editor of choice, create a new C# script, and let's walk through this line by line. So the very first thing we have to do is introduce our script to the rigid body. Right now, our script is completely blind. It has no idea that a rigid body 2D component is even attached to our player. We can't apply torque to something our script doesn't know exists. So our first job, which we'll do in the start method, is to find that component, grab it, and store it in a variable so we can easily access it later, over and over again. And right here, this is the spot where almost every single person new to Unity gets stuck. It's practically a rite of passage. You'll go into your start method. You'll write what looks like perfectly fine code to get the rigid body and put it in a variable. But then when you try to use that same exact variable in the update method, Unity just screams at you with a big red error, usually a null reference exception, saying the variable doesn't exist. So what is going on? Why can't update see the variable we know we just created in start? The answer is a fundamental programming concept called scope, and it's super important to understand. Think of your script file as a house, and think of methods like start and update as different rooms inside that house. When you create a variable inside the start method, it's a local variable. It's like a toy that can only exist and be played with inside that specific room. The second the code finishes running and leaves that room, the toy just vanishes. Update in its own separate room has no idea it ever existed. What we need is a member variable. A member variable is like putting something in the main hallway of the house. Every room can see it and access it. Start can put a value in it, and later, update can come along and read that value. So the correct way to do this always follows this two-step pattern. First, we go to the very top of our script right underneath the class name, and we declare our member variable. We'll type private rigidbody2d rb2d. We're just creating the empty box in the hallway. We're not putting anything in it yet. Then, step 2, we go inside the start method and we assign its value. We type rb2d equals getComponent rigidbody2d. Notice we don't type rigidbody2d again here. We're not creating a new local variable. We're just finding the component and putting it into the existing member variable we made earlier. Now, rb2d will hold on to that reference and be available to every other method in our script. Perfect. Now that we have a reliable way to talk to our rigid body, the rest of the logic is pretty straightforward. We just need to check if the player is pressing the left or right arrow keys, and if they are, apply some torque. Now, your first instinct might be to put this logic in the update method, which runs every single visual frame. But here is a major pro tip. Whenever you are dealing with physics, adding forces, adding torque, anything that affects a rigid body, you should always do it inside fixed update. Fixed update runs on a consistent fixed timer, completely independent of your frame rate. This makes your physics calculations stable and predictable, which prevents all sorts of weird bugs. And here's the code that makes the magic happen. Inside our fixed update method, we just ask a simple question with an if statement. If input.getKey, key code left arrow. If that's true, we grab our rigid body reference and say rb2d.addTorque, torque amount. Then we use an else if to check for the other key, else if input.getKey, key code right arrow. And here's the really slick part. To make it spin the other way, we just call rb2d.addTorque negative torque amount. We just use the same variable but make it negative. One variable, two directions. It's super clean and efficient. Okay, let's pause for a second and talk about that torque amount variable. A really common mistake is to just hard code a number directly into your script, like rb2d.addTorque 10. Programmers call this a magic number, and you should avoid them like the plague. Why? Because it forces you to become a code miner. Every single time you want to adjust how fast the character spins, you have to open up the script, hunt down that number, change it, save the file, wait for Unity to recompile. It's an incredibly slow and frustrating workflow that completely kills your creativity when you're trying to fine-tune the game feel. The professional solution, and one of my absolute favorite features in Unity, is to use the serialized field attribute. Let's go back to the top of our script where we declared our rb2d variable. We'll add a new line. Serialized private float torque amount equals 10F. By adding that little tag in the square brackets right above our variable, we're telling Unity something special. We're saying, hey, I want this variable to stay private in the code so other scripts can't mess with it, but please make it visible in the inspector for me. This gives us the absolute best of both worlds. Safe, encapsulated code, and the incredible power to tweak our game's values in real time without ever touching the code again. Okay, moment of truth. Let's head back into Unity. We have our script, our torque amount is visible in the inspector. I'm gonna hit the play button, press the right arrow key, and it's working, it's spinning, and it's still spinning. And it's getting faster and faster, and oh no, it's a blurry mess. We've just created the infamous death spin. We've successfully installed an engine in our car, but we completely forgot to install the brakes. This next step is all about taming that force and tuning the perfect, responsive feel. So what's our brake pedal? Thankfully, Unity has one built right in. If you select your character and look at the rigid body 2D component in the inspector, you'll find a property called angular drag. This is literally rotational friction. Just like regular drag slows down forward movement, angular drag slows down spinning. Think of it as trying to spin an object through thick air or even molasses. The higher this value is, the more resistance the object has to spinning, and the faster it will slow down to a stop when you let go of the keys. This is the secret ingredient we need. And this is where the art of game development really shines. It's a delicate balancing act between the force you're applying, our torque amount, and the resistance you're adding with angular drag. Let's tune it live. With the game running, I select my character. See here in the rigid body, angular drag is at its tiny default of 0.05. I tap the key, and off it goes into the death spin. Okay, now let's crank the angular drag way, way up. Let's try 5. I tap the key again. Now it feels like I'm trying to turn a giant battleship stuck in mud. It's sluggish and heavy. But what if we find that sweet spot? I'll try a value of, say, 2. I press the key, it turns quickly, I let go, and it stops. Perfectly. It feels responsive, but it comes to a quick, controlled stop. That's it. That's the feel. This is why exposing variables in the inspector is an absolute game changer. Okay, we've done it. We've diagnosed the problem, we've built the correct solution using physics, and we fine-tuned it to feel just right. Let's put it all together one last time, look at the final, clean script, and then really lock in the key principles you should take away from this and use in all your future projects. And here it is, our final script in all its glory. You know, when you look at it, it's actually not a lot of code, is it? But every line is there for a reason, and it's all in the right place. We've got our serialized variable at the top so we can tune it. We have our private reference for the rigid body. In start, we efficiently grab that component just one time. And then in fixed update, the correct place for all things physics, we handle our input and apply the torque. This small, simple block of code is everything you need for a professional physics-based rotation controller. So if you only remember 4 things from today, make it these. First and most importantly, if your object has a rigid body, you use physics forces to move or rotate it. For rotation, that's add torque inside a fixed update. Second, understand variable scope. Use member variables declared at the top of your class to share data between methods like start and fixed update. Third, banish magic numbers forever. Use serial field to expose your variables in the inspector. It will literally change your entire workflow for the better. And finally, remember that good game feel is a dance. It's the balance between the force you apply, like torque, and the resistance you add, like angular drag. And just like that, you've completely mastered one of the most fundamental skills in game development. You're no longer fighting the physics engine, you're now working with it. You're starting to think like a physics-based game developer. And this core principle of applying forces instead of directly setting transforms, that applies to everything. Making a character jump with add force, creating explosions, pushing objects around. The door is now wide open. So the real question is, now that you know how to speak the language of physics and Unity, what are you going to build next? Thanks for joining me.